Hello, my name is Darina Narova, and today I'll be presenting our research on a new patch classification approach for detecting suspicious microcalcifications in mammography. Every day in clinics all around the world, radiologists face a critical decision. They look at mammogram images searching for clues smaller than a grain of salt, clues that could reveal early stage cancer. This task demands precision, speed, and absolute confidence. So, what if we could provide these experts with a trusted second opinion, a tool trained on thousands of cases that could instantly highlight a suspicious area and, more importantly, show why it's suspicious? This brings us to the central question of our research. Can we build a robust AI model to accurately classify mammogram patches as either containing suspicious microcalcification clusters or not? Our team, a collaboration between AI specialists at the University of Chilena and clinical experts at the Oncological Institute of St. Elizabeth, has been focused on this challenge. By the end of this talk, you will see our approach, which delivers not just high accuracy, but also the transparency required for clinical trust. We'll cover three stages: the foundation, our data strategy, the engine, the AI model, and finally the proof, the results that validate our work. A trustworthy AI model must be built on a strong data foundation. We made two critical decisions here. First, diversity. We didn't rely on a single uniform dataset. We combined two distinct databases, the screen film-based CBIS DDSM and the modern full-field digital OMI-IDB. This ensured our model was trained on a wide variety of realistic clinical cases, enhancing its adaptability and accuracy. Second, and most importantly, detail. We resisted the common practice of shrinking images to fit a model. We used large, high-resolution 674 by 674 pixel patches. Why? Because microcalcifications are tiny, and downsampling images leads to a loss of critical detail. Preserving resolution here is essential. This process required significant manual effort to review and clean the data, excluding ambiguous patches and ensuring our negative samples were truly negative. This rigorous curation was key to avoiding the garbage in, garbage out problem. With a strong foundation in place, we needed a powerful and just as importantly a transparent engine. We selected the ResNet 101 architecture, which proved superior in our previous work on mammography classification. We leveraged transfer learning using weights pre-trained on the ImageNet dataset. This gives the model a foundational understanding of image features, leading to faster convergence and better performance. We systematically optimized all key parameters and applied regularization using weight decay to improve robustness. To address the natural class imbalance, we used a weighted cross-entropy loss function. Finally, we employed powerful data augmentation, applying random horizontal and vertical flips during each training epoch to help the model generalize. Our goal wasn't just to build a powerful engine, but a transparent one that doesn't just give an answer but shows its work. And that brings us to the proof. So, how did it perform? The numbers speak for themselves. Our best model achieved a validation accuracy of 98.2%. But in medicine, the details matter more. We reached 99.1% specificity. What does this mean in the clinic? It means fewer false alarms. The model is extremely good at correctly identifying healthy tissue, which reduces patient anxiety and the need of unnecessary biopsies. And crucially, we achieved 94.6% sensitivity. That means we are highly effective at finding what we are looking for. When a suspicious cluster is present, our model is very likely to flag it. This balance between sensitivity and specificity is a sweet spot for a clinical decision support tool. The confusion matrix provides a clear picture. Out of over 2,600 negative patches, only 23 were misclassified. And of the 654 positive patches, the model correctly identified 619, but numbers are only half the story. High accuracy is not enough. Does the model actually understand? Can we trust it? Using a technique called grad count, we can visualize exactly what pixels the model focused on to make its decision. As you can see, the model accurately located visually challenging calcifications and extensive clusters, basing its decisions on the actual suspicious microcalcifications. It also demonstrated an ability to correctly classify patches as negative even when other features like masses or benign macrocalcifications were present, showing it learned to distinguish between different types of abnormalities. Of course, no model is perfect, and analyzing its mistakes is vital. When the model made mistakes, they were often in objectively ambiguous cases, such as patches with a very small number of microcalcifications or those with rare calcification types. But what's most important is shown in the middle image in the bottom right corner. In this example of a microcalcification, the GradCam output showed the model was still looking in exactly the right place. This proves the underlying robustness of the detection mechanism. This level of interpretability is vital for clinical adoption, as it allows radiologists to verify the model's reasoning and moves it from a black box to a collaborative tool. In conclusion, our study successfully implemented a patch classification approach that demonstrates a strong capability for detecting suspicious microcalcification clusters. Our key takeaways are: first, the use of high-resolution patches from two distinct databases with rigorous preprocessing was critical for success. Second, the ResNet 101 architecture achieved an excellent validation accuracy of 98.2%. And third, the model demonstrated robustness by correctly locating clusters even in incorrect predictions, suggesting practical capability in handling visually challenging cases. We believe this model has significant utility as a supportive tool or a third opinion for radiologists. Our future directions include external validation on other datasets to confirm robustness and exploring the incorporation of contextual modeling to further reduce false positives. The AI model and supplementary materials are publicly available on GitHub. Thank you for your attention.